Hello, this is video number 3, Shrinking and Stretching, Algebra 2, Semester 1, Unit 2. Okay. What we've been looking at are specific graphs. Here we're going to start with the linear graph again. First I'll just show you my little cartoon man. I think you guys all probably have heard of the movie, Honey, I Shrunk the Kids. All that we're going to do is take this graph and we're going to shrink him down. Okay, shrink him down to the x-axis, kind of our pond line. He has a lot of control. That domain is the independent variable. He is also kind of the controlling part of this function. And so when we say that we shrink, we're shrinking down to him. Kind of a lot like our drawing here, how he gets shorter, because it's going to come down into that. So I've graphed the parent functions on all of these. Pause the video and go ahead and graph yours on this side of the sheet, and please mark the domain and range while you're at it. Okay, turn back on the video and I'll have mine marked. Oops. Okay, if you're having any trouble with that domain and range, please see me in class. We need to make sure that you are understanding how we get that. Now we're going to take a look at this. We are wanting to shrink this. So we think about this. What do we do to our parent function to cause it to shrink? For example, here we have 1, 1, and 2, 2, and 3, 3. We want to bring those down here, so let's just pretend that we just shrink them. Let's just cut them in half. So instead of 2, 2, we'd want 2, 1. Let's think about that output compared to the input. We have an input of 2, 2 on the parent function, and now we want to go with an input of 2 and come out with an output of 1. Okay, what have I done to my 2? You might say, well, you cut it in half. Just like in the last video, we made sense of when we wanted it to be negative, we just put a negative up there. Well, if we want it cut in half, can't we take x and just say we're going to cut him in half? And that'll shrink them down. Now if we plugged in 4, come over here, 1, 2, 3, 4, instead of coming up to 4, if we cut it in half, we'd be coming up to 2. Let's go out here to 10. Instead of coming up to 10, we'd be coming to 5. That'll work fantastic, won't it? Our domain and range are still unlimited. We've done nothing with that because this graph is going to go on forever and ever, both directions. But what we just did is now when we input, excuse me, when we put in input 0, it's the only one that doesn't cut in half because you can't take half of 0. So it still goes through that origin. But now, when we input 1, it comes out a half. 2, it comes out 1. 3, it would be 1 1/2. 4, it'll be 2. We just shrunk that function, didn't we? Isn't that cool? So we have y equals x, comes up nice and tall, goes right through the diagonals, and when we want to shrink it, we can just put a fraction in here. Put a fraction in there. Today we chose a half, but you could have made it a tenth and really shrunk him, or 3/4 and just barely shrunk him. So that's kind of cool. Kind of cool what happens there. Okay, so now we're going to go with an absolute value. Well, we learned last time we can look at patterns that worked for linear and just try them here. So let's try this. If we have y equals 1/2 of the absolute value of x, we look over at our parent function. When we had 2, it came out 2. When we had -2, it came out -2. Let's try that. Let's plug in 2. Absolute value of 2 is 2. Half of that is 1. So now we would come over to 2 and would be up at 1. 0, 0 is going to remain. Now let's try -2. Absolute value of -2 is 2. Half of that is 1. If we plugged in 4, absolute value of 4 would be 4. Half of that would be 2. So we see our V shape doing this. Look at that. Isn't that incredible? If we put the half in front, we shrunk it down to this x-axis right here on both sides. It makes it look kind of wide, doesn't it? Some people will refer to that as being wide, and I think on your test, I actually have a multiple choice kind of a situation where you have to choose that it makes it wider when you have that fraction in front. So we already know on quadratic what we're going to do to shrink it, because this pattern is working. So we put a half in front of that, x squared, and we could go ahead and just look over here and say, well, I know this is going to make it wide where it's 0, 0. Instead of 1 being squared and being 1, we're going to go 1 squared is 1 and then take half of that. 2 squared is 4, and then we take half of that. So we end up with a much wider looking U. Okay? Now on cubic again, we go with the same idea, y equals a half. And seriously, I could be using, let's even just go there, let's just use a fourth this time. Any kind of a fraction here is going to shrink it. So a fourth, let's look at that one. On our parent function, we had 0, 0. We know 0 is not going to be affected when we multiply by a number. But now 1 cubed is 1. 1 cubed is 1, but then we take a fourth of it. It's way down there. Well, let's go over here. 2 cubed was 8. 2 cubed is 8, but we take a fourth of that, means 2 is only at 2. So if we look at this, wow, that has really, really shrunk our graph, hasn't it? Okay, it just pulls it down. It's like a weight. It's like, whoa, pulls it right down to the x-axis. So with our new transformation here, our domain and range are still unlimited in cubic. Pretty common trend that we see with cubic. He just doesn't withstand any limitations. But in our absolute value, forgot to put the arrow tips, but we do see that the bottom limitation does stand, so y is greater than or equal to 0, and the domain still is unlimited. Quadratic, unlimited domain, and the y is still greater than or equal to 0. So we don't see where it really made an effect on the domain and range. They stayed pretty much like the parent ones. But you can see, wow, that is just so cool how it shrinks down. Now I do ask a question down here. You look at these. I want you to do this on your own. You're going to identify the shape. And then you're going to identify how much it is affected by this number in front. Tell me how much it shrinks it down. Give me a couple points, for example. Then I ask which one shrinks closest to the axis. Well, as we can see up here, when we went half, 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 and then we went a quarter, and a quarter really brought it down closer. It's the fraction that's closest to 0. So you're going to have to evaluate which of these numbers or decimals is closest to 0. I do want to see that when you come to class. Make sure and check in with me on that. Okay, next thing is, and I don't know why they didn't do a movie of this. Maybe they did. I don't watch movies really, but wouldn't it have been cool to have that movie, Honey, I Stretched the Kids, and have them stretched out like silly putty. If you've never played with silly putty, I've got some in my cabinet. Come in and ask me. I'll let you play with it a little bit. It's really fun. You know, you can press it down and get an imprint and then stretch that imprint. And it's just fun to look at and see how it goes. We're going to do the same thing here. Remember, we always look at that x-axis. I wonder if that could possibly be because this is a function of x. You might think about that a little bit. So again, our domain and range, let's fill those in quickly. Go ahead and pause the tape and fill yours in. Okay. So this time we want to stretch it up. Well, we know when we shrunk it that we put a fraction in front. So that might give us a clue of how we're going to manage to get this stretched is something to do with a number in front. So if our point here is 1, 1, and now let's say we want to stretch it. Let's say we want to pull it way off of this x-axis, and we want to go from 1, 1 clear up here to 1, 3. Whoo, we're going to really stretch him. Just pull him straight up in the air that way. Well, we now want it to become 1, 3. So we take our parent function, which was 1, 1. We say, well, we want to make that y value become 3. If this is a 1, we can simply put a 3 in there and multiply it by 3, we'll get the 3 value. Now let's check it out and see if it works for 2. If we plug in 2, 2 times 3 would be 6. And if we come over to our parent function over at 2, it was 2, 2. Whoo, it goes up to 6. That's exactly what we're wanting. So we see by what we've just done, sorry, this paper gets kind of in the way with the tripod leg. So what we've just done is we've gone 1, 3, 2, 6, and we know it's linear, so we can connect our line. Look at this stretch. Oh my gosh. We just pulled him clear off that x-axis, didn't we? So the parent function, we accomplished what we wanted. We wanted to pull him up, stretch him away from it. We've got him stretched away simply by putting that 3 in there. Okay, the domain is not affected. It's still real numbers. The range is still real numbers. Okay, now we go to our absolute value. Well, we know from past experience in math, we can use patterns that have worked on other functions and see if it works here. So let's just try absolute value of x equal to y and stick a 3 in front of it. We know the absolute value of 1 was 1. Absolute value of 1 is 1, and then we multiply by 3, so we get the point 1, 3. Absolute value of negative 1 was positive 1 because it's the distance from 0. But now we multiply it by 3, and we get that the absolute value is 1 times 3 is 3. So we've just taken our parent function. Instead of coming over 1, we go over 3. Now if we were to put in 2, absolute value of 2, it's 2 units from 0, then multiplied by 3, that's going to be 6. Same thing on the negative. Look at this V shape stretched away from the x-axis. Oh my goodness, look at that stretch. It's become very, very skinny, hasn't it? And we can say that it's stretched or that it's skinny. I hear the term compressed on the shrunk, or when it shrinks. I'm not sure if they use the word expanded, but you could think of that it's expanded away from the x. The range, again, it's still y is greater than 0, domain is unlimited. So now we already know with our quadratic, we can stretch it. It's going to come up here and be stretched really steep. Now on these, it's real hard to show me that it's a U. You gotta work at showing me that that's a U when it's stretched, because it's really skinny, okay? And plug in points, make sure that it works. When 1 is squared, it's 1 times 3 is 3, okay? If we square 2, it's 4 times 3. Whoa, we're off the graph. It's 12. We've like stretched it clear into space. Okay, so y is greater than 0, and the domain is all real numbers. Okay, next one, cubic. Again, we're going to go with the same pattern that's been working. And we see in our parent function it looked like this. We were at the point 1, 1. Now it's going to be 1 multiplied by 3, because it's 1 cubed. That 1 now has an output of 3. Negative 1 cubed was negative 1, because negative 1 times negative 1 is positive 1, times negative 1 is negative 1, times 3 is negative 3. So we've just taken our 2 points right there by the vertex. Of course, 0 multiplied by anything is still 0. But now we go 1, it's clear up here at 3. Negative 1, it's clear down at negative 3. Oh my goodness, before our 2 was at negative 2 was at negative 8. If we took that and multiplied it by 3, that would be negative 24. We absolutely took it clear off our visible viewing area. So it's really stretched away from that x. Hopefully we didn't dislocate anything as we stretched. So all real numbers on both our domain and range. I would like you to look down here. Now this time I want you to identify whether it's stretched or shrink. Okay, this is page 5, so I want you to do the bottom of that. And then what I'd like you to do is this next page, page 6, you're going to put the parent graph over here, just like we've been doing on the left-hand side, and show the equation. And then I tell you that I want you to shrink by 1/3 and reflect. Ooh, I put both of those together. So, sorry, I didn't realize I was off of here. Okay, so you're going to have to show me how to get that 1/3 shrink and how to get the reflect. I'll give you a clue. You could go ahead and write your x here, because everything else you do is going to be up here in front. So see if you can figure it out, plug in a couple points, make sure that you get what you want. That's a really cool one, because instead of it being up in the first quadrant, you're going to be reflecting it into this fourth quadrant and shrinking it up to the x-axis. Do all 3 of these, and then come down and do a few of these. Actually, I'll do the first one with you here. Transformation from the parent function, well, the only change that we see is we have a 4.5. 4.5 is bigger than 1, so that would have to be a stretch. We saw the shrinking only occurring with fractions less than 1, so this would be a stretch by factors are when we multiply, of 4.5. Okay? Shape, oh, well, we look back, the x, it's not got the absolute values around it, so it's not a v. It doesn't have the square, so it's not a u. It doesn't have the cube, so it's not the s. It's just a plain old x, which means it's linear. Straight line. Okay? I would expect you to do all of this page 6 by yourself. Check with me, make sure that it's correct before you go on. We'll see you in the next lesson.